In many physics problems, there are strings. Now, strings in physics problems are usually what are called physics strings. These are not the same thing as real strings. And we'll talk a little bit about this as we go on. A physics string is an idealization. It is a model. And what makes a physics string unique, and the reason that we use them is to make the problem simpler. They are unique because they have certain properties, and here's the properties that they have. First property is that in a physics string, we're going to assume that the string is massless, and we're going to assume that it's unstretchable. Now, no real world string does this. If you stretch on a cable, even a steel cable, that cable, if you can measure its length, will actually increase. It gets stretched. And that means that if two objects are attached by that string and you pull on that, one of those objects can move while the other doesn't. We're going to assume these are perfect, wonderful physics strings, better than anything in engineering anybody can make. And that because of that, if one of those blocks moves, the other block will have to move. We're going to make it unstretchable. The other thing is they're made of atoms, and so real world strings, cables, have mass. In fact, something like the Golden Gate Bridge, the cables of that bridge in a suspension bridge actually have more mass and therefore constitute a larger part of the weight of the bridge than does the level area that it's holding up that the cars drive across, or even the metal scaffolding that's stuck deep into the water. People don't think about that, but the strings are a substantial portion, that's the big cables, of the weight of these bridges. Well, we're not going to consider that. I'll tell you later how we could handle it if we wanted to in more advanced courses, but for now we're going to assume that our strings are close to being massless. That is, they're real thin strings like what you have in your labs of your schools, as compared to the objects like the carts and the weights that you hang on them, and we'll assume they're unstretchable. Now, these properties make the physics problem easier to solve because they tell us some things. And here's what they tell us. They tell us that the magnitude of the force on the physics string is the same at both ends of the string. I'll prove that in just a minute. And that if two objects are connected by a physics string, they must have the same velocity and acceleration. And I'll show you how we can adjust our coordinate system so that we account for any directional change in the string. All right, so let me show you how this works out. The first one is I'm going to assume that the string has mass, and if it had mass, what you would do with the string is you would replace it when solving the problem with a free body diagram. And on one end of the string, there would be, say, a tension, a force T2. And the other end, there'd be a force T1. So what I'm talking about is like you might have a block here, and this block's attached to another block on a string. There's my string. And what I've done is drawn the free body of that string. And on this side, this block is pulling on the string with a force T2. And on the other side, that block is pulling with a force T1. I know the direction of these forces because of something else I'll put in your notes a little bit later, which is strings can't push. In other words, the string has to pull this way on the block. Therefore, the block has to pull the opposite by the third law on the string. So that's how I know these directions of these two forces. And let me go ahead and let me make an XY coordinate system. Sum of the forces in X will be the mass of the string times the acceleration in X, and the free body diagram says that's T2 minus T1 is the mass of the string times the acceleration in X. So in general, if there is no acceleration, so that this side is 0, then T2 is equal to T1. But if this two blocks here are accelerating, and hence the string is accelerating, then AX will not be 0. And if the mass is not 0, then the right-hand side will not be 0. Maybe it's 10. If it's 10, then T2 will be greater than T1 by 10. So the force on the two sides will not be the same. However, if the mass of the string is 0, if this is 0, then even if the acceleration was 12 meters per second squared, 12 times 0 is 0. And that means then that T2 is equal to T1. Only if ms equaled 0 or AX was 0. So either you have to have a problem where there is no acceleration, or you have to have this where this mass was 0. Also, if this was hanging vertically down, say this way, then gravity would be pulling at different places, and it turns out that there would be this tension up here would have to hold up more of the weight of the cable than the bottom would be. This is another really neat, tricky problem that we can get into, but we're going to, for now, this part of the course, ignore these type of tricky problems. They're generally ignored in the UIL contest. They're generally ignored in MCAT exams for people going to med school. We're going to ignore those type of problems, except for those who want to go on to, say, engineering, especially the calculus-based courses, and we're going to simply assume that all our strings, unless told otherwise, are massless strings. And the way they usually do that is they just say strings, or they say it's a physics string, so it would be massless. The other thing is, if this was a rubber band, if it would stretch, then you could pull this mass while you kept that mass stable. So this could have a velocity and that mass not. With a physics string, if this guy is held, since this doesn't stretch, this person can't move. If this person moves 1 meter, that block has to move 1 meter. If this block moves 1 meter in 1 second, that block moves 1 meter in 1 second. That means they have the same velocity. Furthermore, if this velocity changes, this guy's velocity has to change. So they have the same acceleration. So, going back, this property of the fact that it is massless is what gives us this. So let me put that kind of down. This is due to massless. And this is due to it being unstretchable. Okay, let's see how we can use those properties to solve some things for us. Let's say that we have the following set of masses. You have two masses, M1 and M2, connected by a rope with T equal 10 newtons. Since they're connected by a physics string, we know certain things. We'll know that they have the same acceleration. And furthermore, because they have the same acceleration, we could consider them just to be a single body. And that single body would have a mass of M1 plus M2. So I'm going to show you a trick to working this with this fact that I know that this M1 and M2 can be treated as a single body. What I'll do is, instead of breaking this into two free body diagrams, which I'll do in a minute as well in the next video, I'm going to just draw it as a single body diagram. And personally, I like to kind of put down something like that that shows it's separated. So we have weight 2 here. We have weight 1 there. And we have a tension, T. And that's the free body diagram of this problem for the single new unified mass. Notice what's gone away. What gone away, if you draw it this away, was this string. Why is that? Because Newton's law says you don't care about internal forces. And if I draw this as a single combined mass, then this is an internal force and doesn't enter into Newton's laws. Reading my equation here, I have the sum of the forces in X is equal to M total times AX. The force, I'm told, is 10 newtons, which is T. The mass is M1 plus M2. So AX is T over M1 plus M2. Go back up here and put in your numbers to the problem. You have a 10 Newton for T. You have 5 and 3 kilograms respectively for the mass. That's 8 kilograms. So I have 10 newtons over 8 kilograms. And I punch my calculator. And I get 1.25 meters per second squared. And so I was able to find the acceleration without ever actually finding the tension in the middle rope, just by knowing the pull of the outer side, because I knew that the object could be treated as a single object because the string did not stretch. Now, in the next video, I'll finish this problem up by going back here and resolving this by treating these free bodies, these two masses, as separate bodies with their own free body diagram. This is the way most people do it, and you have to do it that way if you want to find the tension in this rope. But by understanding Newton's law and understanding that I could treat the whole thing as a single body, we're going to see that I have saved a whole lot of algebra. And again, it's a trick. You always have to know tricks, but knowing the tricks can enable you to work problems faster. All right, I'll see you in the next video.